So here's a simplified diagram showing the first phase or stage of glycolysis, the energy investment phase. Sometimes it's called the preparatory stage, but really this is the stage where we're just having that investment of ATP in order for that to pay off a little bit later. This is a lot of information to look at once. So what I'm going to do is I'm going to put up my screen and hide parts of this as we go. All right, and hopefully this will show up on my video. As it turns out, it does show up. I just had to check that quickly. So as you can see here, I'm starting off with a 6-carbon molecule. So each of these balls are meant to represent a carbon atom. We're ignoring some of the fancy stuff that's in the structural molecule so that you're not focusing on all the messiness of it, but on the core principles or ideas, the parts of it that really matter at this stage. So that glucose molecule, we want to be able to break it down. And so the first thing that we need to do in order to make that happen is we need to energize that glucose molecule. We need to make it a little less stable so that it wants to break apart. And so the way that we do that is by investing one molecule of ATP, taking a phosphate group off of it, and rendering it as a simpler molecule of ADP. That phosphate that's removed from ATP is tacked on to glucose molecule and forms a new molecule called glucose 6-phosphate. So that's our next phase. So let's continue on with this. So, this molecule of glucose 6-phosphate is not quite unstable enough to want to split apart. And so the second step involves a couple of different things that are going to help to promote its ability to break apart. And the first one of that is that it forms an isomer of itself. You'll remember the word isomer means like iso meaning like similar or same. Or the version of. So all that happens is glucose rearranges itself into fructose. If you take a look in your textbook at the appropriate diagrams, you'll see that although these simplistic representative diagrams don't really show any change, they look identical, in your textbook they will actually look the same, or different rather. Okay, so glucose 6-phosphate becomes fructose 6-phosphate. And in that rearranging, we end up with a less stable molecule. It also makes it a little more symmetrical. Instead of having that sort of off-centered glucose with the oxygen on one side, we now have the fructose with the oxygen in that pentagon sort of form. And so now what we're going to do is to invest another ATP, and in doing so we're able to use the phosphate group removed from ATP and add it on to that existing fructose molecule. And so now we have a fructose 1,6-bisphosphate molecule. Okay, so the bis is another prefix that can mean 2. Some diagrams will call it diphosphate, but most of the biology textbooks that I'm familiar with will call it fructose 1,6-bisphosphate. Okay, so let's just recap from the beginning. We've taken glucose, we've added a phosphate to it and formed glucose 6-phosphate in the goal of trying to get it to become unstable. And then, in order to further that instability, to help it to break apart, we're going to isomerize glucose into fructose 6-phosphate. And then we're going to add another phosphate group to the fructose 6-phosphate, forming fructose 1,6-bisphosphate. So now we've got 2 phosphate groups. This molecule is holding a lot of energy, and that's going to make it extremely unstable. So let's write a little bit of this down. So this is the part where that I really think it's important for you to go through the process of writing this down, just to kind of help you integrate it into your brain, and then we'll go back after you've written it and recap. So again, we're at the energy investment phase of glycolysis. And so in those first 3 steps, and I hope that you're also sort of looking at the diagrams as we're writing this and referring to them as we speak about it, just for frame of reference. So the whole point of steps 1 through 3 is that we're going to take that fuel molecule, glucose, and energize it, make it unstable so that it'll break apart. And we're going to do that using ATP. Okay, so overall what we've done is we've taken 3 chemical reactions and we've taken that molecule of glucose, we've created some intermediate molecules. Remember, we created glucose 6-phosphate, then it isomerized to fructose 6-phosphate, and then finally to fructose 1,6-bisphosphate. And in doing so, we had to invest ATP to phosphorylate those molecules and make them unstable. So as you noticed, hopefully, this is just a reminder for later on that those arrows that you see that are coupled basically describe that you're inputting an ATP, removing a phosphate from it, and creating it and adding it onto another molecule, and that results in an ADP molecule that is released. Okay, so again, the last thing to discuss is that in those steps, in that investment or preparatory phase, we're investing ATP molecules, 2 of them, in order to make glucose less stable and cause it to break apart, to want to split. Why do we want it to split? Well, remember that the overall goal of glycolysis is to end up with 2 3-carbon molecules of pyruvate. And so in order for that to happen, glucose, the 6-carbon glucose, does have to split. All right, so going back to where we left off with our fructose 1,6-bisphosphate molecule, and it's super unstable with those 2 phosphate groups there. Not too happy of a molecule, and so it's so unstable that it in fact does split into 2 molecules. So it splits into a molecule of DHAP, dihydroxyacetone, and glyceraldehyde 3-phosphate. I'm actually going to go ahead and write in not just GP, but G3P, because never in my life have I ever seen glyceraldehyde 3-phosphate referred to as GP. Most textbooks, I think yours does in fact, refers to it as G3P. So that's, a little weird to me, but anyway, here we are. So let's talk about this. So if you look on your diagrams in your textbook, you'll see that there are some structural differences when fructose 1,6-bisphosphate splits. It splits and the 2 pieces aren't exactly equal. And so the one piece ends up being this dihydroxyacetone phosphate, and the other one ends up being the G3P molecule. But this weird sort of thing happens where almost immediately, if your body needs energy, the DHAP will isomerize and convert into a G3P. So really what we have moving forward to after step 5 are 2 molecules of G3P. So again, DHAP almost immediately converts into a G3P so that it can move on in the cycle if your body needs energy. Now, your body doesn't always need energy, so that's why this is listed as a reversible reaction. So in times where your body doesn't need energy, sometimes the G3P molecule will get converted into a DHAP. And the reason that happens is because DHAP is kind of stuck. It can't move on into the final payoff stages of glycolysis. It has to stay there. So think of DHAP as sort of like the hibernating form of G3P, and when energy is required, the G3P molecule will move on and the DHAP molecules will be converted into G3P molecules so that they can be used to produce more ATP. So let's get some of this written down. So in step 4, once we've created that fructose 1,6-bisphosphate molecule and it splits, then we're ready to move on to the energy payoff stage. But let's get a little bit of this down for later. So remember that fructose 1,6-bisphosphate is highly reactive, and it's going to break into 2 separate molecules, the DHAP and the G3P. If there's an energy need, the DHAP is going to immediately isomerize to G3P. just break this up a bit while you're probably writing this down. And I'm going to bullet this because it'll just look a little prettier for you guys. There we go. That's better. All right, pause the video if you need to get all of this down.